Hi class, this is Russ. So I thought we would resume our discussion on implementing the bag using a linked list, singly linked list type data structure. And so this is the third sequence of the uh, videos that I'm posting for module 2. And the only things that are left are to deal with the remove and clear functionalities of the linked Java bag. And then of course we need to test it. So we're working on linked bag, and so we could start off with a clear method since that probably requires the least work. And so the clear method, all this will do is simply remove all the items from the linked list and therefore the bag. So it's going to, okay, so what we can do is we can say while not is empty, since is empty is the Boolean check um, for items in the bag. Okay, so in other words, while you still have items in the bag, what you can do is you can remove. Okay, and remove is basically, we'll discuss that right now. So what does the remove method accomplish? Well, so the remove method right here, all right, and this is where comments are essential. Okay, so the remove method removes one unspecified entry from the bag. Unspecified entry from the bag if possible. Okay, and so the remove methodology, all it does is, uh, let's see, what can it possibly do? Okay, so it returns a generic uh, class, and so in this case it'll return a boutique items object. Okay, but in this particular module, uh, since T is generic, it'll return any object that we're dealing with, whether it's the specific um, boutique items or any object of your choosing for a different project. So, so what we'll do is we'll define the return as a generic type T. Okay, T result, and we'll initially we'll initialize it to null. All right, and so if um, first node, okay, remember the first node is the first element in the linked list. So if it's not null, okay, so what can we do? Well, we assign that value to result. So result, okay, so we could say result is equal to first node dot data. So recall now what we mean by these items. Data, okay, so data is actually the object instance of a boutique items class. And first node is the data plus the pointer to the next node in the linked list. All right, so we go to first node, pull out the object instance, and assign it to result, since result is the generic type T. Okay, then once we do that, to get rid of first node, okay, to unload it and readjust our linked list now to exclude the first node, we take our first node and we assign it to the next item in the list. Okay, and so and so what's interesting here, this is what's interesting compared Java as compared with C sharp, something like C sharp or C++. Um, Notice that we didn't deallocate the memory set aside for this piece, the original first node. But it's actually destructed. They're behind the scenes, and I don't know if the book mentions this or not, but behind the scenes, there's a Java virtual machine runs a thread or a process called a garbage collector. Okay, and as soon as this first node is pointing to the second node, the memory allocated to the original first node is freed up. okay? But the contents to the original first node are still there. And result is essentially a copy of the original first node. So you still have resources, or not, yeah, you still have memory resources that are pointing to a first node, but the garbage collector will intercept this and destruct it, free it up so that the memory can be used again. Okay, and that's not wasn't made too clear, I don't think, in the chapter. So okay, and so once we scratch the first node and move it to the second node, then we have to decrement the number of entries in the linked list. Okay, so there are a lot of things going on in this particular case. All right, and then once we extract our result, then we have to return result. Okay. All right, so that's the remove of basically the head of the linked list. So the remove option essentially removes the head of the linked list as long as there is a linked list. All right, so now we need to address a more complicated issue, and that is removing an ad hoc entry from the linked list. So Boolean result equals false. Okay, I'm going to declare a Boolean, and um, so what I need to do is, since before I explain this, we need to identify in the linked list where this particular new entry is. And so what we do is we declare a method called getReference2. Right, so we need to pull a reference to this particular entry that we're trying to delete. So where is that? Let's see here. It's in the book somewhere, I believe, or possibly in my notes. Let me check. What's the efficient way? Yeah, get frequency, scanning, get frequency, um, contains. Yes, here we go. So we need a private class method to identify a particular node in the linked list. So before I proceed with this method, we need an augmenting method to identify new entry, okay, which is some ad hoc node in the linked list. So what I'm going to do is private class, private that returns a node, okay, that will be object instance plus a pointer, okay, get reference 2, okay, and we pass to it our candidate node. All right, so basically we're checking to see if a particular node exists in the linked list, and if it does, we'll return a reference to it. Okay, so Boolean found equals false. Okay, node current node is equal to first node. Okay, so we put a pointer to the first node. Okay, and I'm checking. Yeah, sorry. I'm checking to make sure I haven't addressed this already. Okay, so now we say while not found and, okay, and current node is not null. Okay, okay, if an entry, okay, equals the current node, okay, object or data instance of class T, okay, then we set what? Found equals true. Okay, found equals true, else, okay, current node goes to the next node. Okay, and note that next is again it's like data. It's an object of boutique items in our project. Okay, and so once we identify this, so either current node is going to be a node in the linked list, or it's going to be null. Okay, and so then we return current node. Okay, and I suppose rather than iterating through the whole list, okay, we can break once we find it, right? So we can do that. We don't need to, because if this list has 10,000 elements and the one we look for is the third element, we don't need to go through 9,997 comparisons, right? Once we find it, we're done. Okay. All right, so now we can go back to the business of removing our current entry. All right, so removing an ad hoc entry. Check that. So let's go back to the implementation. So what I'll do then is I'll go node node n is equal to a reference to the entry which we are attempting to remove. Get this dot get reference to an entry, new entry basically, right? Let me check that. Let me change this. Yeah, I'm going to leave that like I'm going to change the parameter to an entry. Okay, since we're going to remove some ad hoc entry as opposed to a specific new entry. Okay, so we stuff the entry that we're attempting to remove into a new node. Okay, and what next? So if node n is not equal to null, okay, then so what we'll do is we will replace the located entry, okay, with the entry in the first node. Okay, so we'll take the first node and we'll move it into the location where this node that we're trying to remove currently exists. Okay, so here's how we do that. So node in dot data, okay, is equal to first node dot data. Check that first node. First node. Yes, first node dot data. Okay, and now we need to adjust the references to the next node. So first node, the first node equals to the first node dot next. Okay, so what this does is it removes the first node. Okay, all right, and then we decrement the number of entries. Okay, so that's kind of clever. Okay, you assign the entry you're trying to remove to the first node. Check that. You remove the first node. You move the first node into the location where of the entry you're trying to remove, and then you lop off the first node. Okay, so you kind of play a shell game, a sliding game, and then result equals true. Okay, all right. So now of course, if the node that you seek to remove is null, then you just return result, which is initialized to false. Okay, so that's how we deal with removing an ad hoc node from the linked list. All right, so this is way too cool, right? I mean, we don't have any numbers. We're not constrained by any logical limits on the size of our bag. Well, of course, we keep track of the number of entries, but so what? As long as it's less than the size of an integer. How big is an integer in Java? What does it go up to? About 2 million or so, or I don't know, whatever the upper bound is for an integer. Yeah, we could sit here all day and just, or until we run out of memory and stuff things into our linked list and remove things from our linked list and never worry about any logical bounds. All right, so that's the removal functionality of our linked bag. And so I guess we need to test it now. So in our boutique, okay, so our boutique now, our boutique items class is now what? A linked bag. So we'll call this a linked bag. And I think that's all we need to do, really, right? Linked bag. Well, so we should test this. Okay, so boutique driver, boutique items. Okay, that's the class that holds. This is an item in the bag. Okay, all right. So let's launch. See what happens. So that's all we had to change, right? The power of object-oriented programming promotes extensive code reuse if it works. Okay, so let's add an item. Okay, so shirt and the cost $1.23. Let's add another shirt. Let's make it $1.24. Let's add another item, pants. Let's make it $2. Let's add another item, shoes. Let's make it $10. Let's add another item, say dress. Let's make it $5. Okay, so let's print the contents. So what do we have in our bag so far? We have 5 items. Okay, so now let's remove an item from the bag. Okay, notice that I'm not testing all of the functions of the linked bag, such as remove everything from the bag, or I'm only removing a specific item from the bag, and I'm not checking the size of the bag. Well, I am, I guess, in essence, in the print method. Okay, so let's remove. Okay, so let's remove. What's a good item to remove? The pants. Let's remove the pants, and the pants cost $2. And what is it? Successfully remove the item. All right, and so let's print the bag to make sure that there are no pants in the bag, and it doesn't appear to. So let's move the let's remove the shoes. Okay, and the shoes cost what? $10. Okay, print the bag, and there are no shoes. Let's remove the cheapest shirt. Remove shirt, $1.23. And the $1.23 shirt is gone. Let's remove the $1.24 shirt. Okay, and so the only thing left in the bag is the dress, so let's remove the dress, which is $5, right? Okay, and there's nothing left in the bag, so if we attempt to remove, so let's try and remove what? Socks. 99 cents. Okay, failed an attempt. Okay, so now the bag is essentially null or empty. So let's go back and add socks to the bag. Socks, 99 cents. Okay, and there they are. Okay, so there's your fully functioning bag, and it's very robust, right? Although it's probably not the most efficient implementation. Probably a more efficient implementation of a linked bag would be something to use a hash bag or a binary search tree bag. That's probably what Amazon uses, or any kind of online shopping cart function. It'd be interesting to know. Well, anyway, there's the opportunity. So I believe this closes out our discussion for chapters 2 and 3.